Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will have another case of skin modeling and also skin improvement due to workover, due to perforation addition. And if you have checked my previous videos in this WellFlo playlist, in that videos, we we get skin reduction and we get productivity improvement. But first we do modeling, I mean matching, productivity index matching, and we adjust the permeability in those videos. In those cases, we adjust the permeability. We obtain permeability from, for example, log, log analysis, log evaluation, and we say that there will be uncertainty on the log evaluation, and we did the adjustment. But in these videos and maybe in the next several videos, we will do productivity index matching, not by adjusting the permeability from well log, but by adjusting the skin or the measured crushed skin. Okay, we will understand that better if we arrive at the section later, IPR or reservoir section later. So this is the case. Currently, we are at the dashboard. So you can see we have ESP model here, and we can check the well and flow type. It's a producer well with electrical submersible pump, flow type tubing, fluid type black oil, well orientation vertical well, and then we go forward. Flow correlations, it's quite basic. We use Dance and Ross correlation, and then for the reference depth, based on the KB, Kelly bushing, and the distance from the KB to the wellhead is 17.14 feet. So all the depths that we will input later, it's basically measured from the KB down to the depth. Okay, so the KB to wellhead depth is 17.14. So later on, all the depths must be depth in KBMD, Kelly bushing measured depth. All right, so we go forward, and this is the fluid parameters. So we have oil with oil specific gravity of 0.84, with oil gravity in API degree 36, gas specific gravity 0.7, water salinity 33,000 ppm. Okay, 30,000 ppm. Water gravity will be calculated, and you can open and calculate for the PVT data. Go down here. We input the reservoir pressure, we input the reservoir temperature, and we input the produced GOR. We calculate, we obtain all the properties out, the bubble point, the oil formation volume factor, the solution gas oil ratio, and so on and so forth. And we can also generate the chart, right? Just by inputting the upper range and lower range. For example, 14 PSI 8 to 900 with 10 steps. Okay. And also yeah, it's okay. We can minimize that section. Temperature, okay, like this. Cannot. Maybe, yeah, 60 to 180. Lower range pressure should be less than the upper range. Oh, sorry. It's 914. like this. Okay, so we can generate the gas viscosity and the gas C factor. All right, and then we can also plot the produced GOR like this, and then the oil viscosity. So I just input the upper range, for example, the upper range of the reservoir pressure, and I'm interested to know the properties down to 14 psia at atmospheric condition, and just input the steps. For the temperature, I'm only interested in 180, the reservoir temperature. So I just need to use one step. All right. And currently I'm plotting the oil viscosity and lastly the oil formation volume factor. So like this. All right. Later on, our main section will be in the reservoir section. But before that, I will show you the wellbore section first. Okay. Go to wellbore at deviation. So we have a deviated well, measured depth through vertical depth, and the segment deviation from vertical will be calculated automatically. And this is the sketch. And the equipment, it's quite basic. We have, of course, the tubing, all right, with single size diameter, internal diameter of 2.441. And for the casing, it's like this. And we also input the temperature model by inputting the surface surrounding temperature of 83 degrees Fahrenheit. And this one, the U, will be calculated. And the ESP data, we use the 1050N REDA pump with 101 stages and pump wear factor 0.66. It's not a new pump. So we input the pump wear factor accordingly, and all the ESP data, ESP properties, you can see here in this section. All right, but our main discussion will be here in reservoir section. So you can check my previous videos. So our strategy is like this. We have actual productivity index from well test, right? And we can input in WellFlo in this section, taste data section. And we got productivity index, the actual productivity index based on well test for this well. The PI, the productivity index is actually 3.2 stock time barrel per day per PSI. Okay, so first I want to match that productivity index using my analytical model. So I create this match existing section. So it will be a model reservoir. I input all the reservoir properties, and I expect that I will get productivity index of 3.2. If I cannot achieve that, I will adjust a parameter or two in such a way that I will get productivity index that is similar, that is equal to the actual productivity index obtained from well test. Okay, so currently you are looking at my productivity index. It's still 3.7. So I need to adjust a parameter so that I can get productivity index of 3.2, similar to the actual PI, productivity index, based on well test. Okay, so let's see. So the reservoir pressure, 829.7. I believe this one. I trust this value, so I will not adjust that. Reservoir temperature of 180 degrees Fahrenheit, so I'm okay with that. Mid perf depth, middle of perforation. Let me check. Okay. So this is This is the real number. So of course, I will not adjust this value. Okay, it's given. Permeability from lock based on the evaluation, it's 141. I can adjust this one because of course, permeability from lock not necessarily represent all the drainage area of the well. Okay, so maybe we can adjust that, but we did that strategy. We used that strategy in previous videos. In this video, I will assume that I can trust my permeability from well lock evaluation, and I will adjust another parameter. All right. And the net pay thickness based on lock evaluation, it's 129, and wellbore radius 0.4, water cut 0.98 or 98%, gas oil ratio 300, and Vogel coefficient 0.2. I use calculated skin, drainage area assume 250 meters, and I don't think I will adjust this drainage radius. Okay, so I will assume the radius, the equivalent drainage radius to be 250. All right, and then let's go to the skin. We will play at this section. We will do the adjustment at this section. All right. So the completion type case hole, damaged skin. I actually can input and can do adjustment in this section, but it will be very difficult because I don't have any idea. I don't have any measurement about it. For this one, I don't know the damage zone permeability. I don't know the damage zone thickness. I don't have the laboratory study for that. So it will be too uncertain if I use that for my adjustment. So I I prefer unchecking this one, and I will do adjustment on another property. Okay, so that will be the strategy here. Nearest measured formation distance, 26 feet. I measure this one from top reservoir to the top perforation, right? So the distance from the top reservoir down to the top perforation, it's 26. Vertical permeability, assuming 10% of horizontal permeability, so it's 40, 14.1. It's 10% of 141. Open interval, it's 32 feet. So the calculated limited entry skin is 21. And deficient skin, it's 45 degrees with vertical permeability of 14.1. So the computed deficient skin is minus 0.44. It's minus, but it's not too big. Perf diameter, I use perforation table. Okay, perforation data from the perforation company. So I used that table and I input it here. Okay, and I don't think I will do adjustment for these parameters because yeah, there will be, yeah, it's quite difficult. It's engineering thing. If you have data, if you have certain information, it's better if you can keep that. It's better if you can honor that information. So I get the data from the table. I use that for my computation, and I will do adjustment on properties that I have, that I'm uncertain about it at the highest level compared to another or compared to other properties. Okay, so let's assume I believe the perforation properties, shot penetration. I also use the table. The table says it is 39.6, so I use that. Okay, of course I can do adjustment, but yeah, I can do adjustment in any other property. So I decide to do adjustment not in shot penetration, but in another property. All right. And shot density, it's 5 SPF, shot facing 60 degrees, and using the flow shape factor based on log, the perforation skin is 33.77. If I use tarik, it will be change. All right. Muscat also change. And yeah, if you want to know about log again, tarik, and muscat, yeah, you need to go back to the literature. And in the study, I used tarik. All right. And the productivity index is 3.52. Right. It's still not matched with the actual productivity index. The actual productivity index is 3.2. So the thing that I want to adjust is actually this one, measured skin. So I will use this measured skin as the thing that I will adjust in such a way that I can match the productivity index. So I will maintain other properties based on the data, based on the table, based on the evaluation. And the thing that I don't know very much is measured skin. So I will use this measured skin as the adjustment parameter. All right, so that will be easier. In previous videos, I adjust the permeability. So although I already have permeability from log evaluation, I decided to still adjust the data to get match productivity index. But I think I will use better strategy here. So I will honor the permeability from log evaluation, and I will adjust the measured skin. All right. So let's try measured skin of 5. Yeah, in real life, it's very difficult to know the measured skin. Okay, in real life, it's very difficult to know the measured skin, if not impossible. So I think it's better if we can adjust the measured skin to get match productivity index, right? So let's input measured skin 5, and it's still a reasonable value. And we get productivity index of 3.22, which is already very close to the real productivity index. All right, so I will save this one. So other properties are maintained, other properties are kept, log evaluation, perforation properties are kept, but I adjust the most uncertain, the unknown thing, which is the measured skin. All right. And yeah, now the productivity index is 3.22. So that's the thing. And yep. So from this one, this is the condition, the existing condition before the workover. So now we do the prediction. What will happen after I do the workover? What will happen if I do additional perforation? Okay, so my skin will be changed. So we create after job. We maintain the pressure, of course, temperature. Now the middle perforation will be shifted. Okay, previously 3154, and I do additional perforation at the upper side of the existing perforation. So I will do shift up. So the middle perforation will be shifted up, okay, to the upper side. And the middle perforation after the workover will be 3142.5. We maintain the permeability, of course. We maintain the thickness, of course. And here's the thing. We do the shift up perforation. We go to the upper side, and it's sort of we open the attic oil, we access the attic zone. So we expect that we will get better water cut. We expect that we will have lower water cut. So I assume, let's say, the water cut will be reduced from 98% to 96%. Okay. Yeah, that's the expectation. If we go to the upper side of the reservoir or to the top side of the reservoir, we expect we will get reduced water cut. Okay. And the gas oil ratio 300, drainage area geometry still 250, and the skin now will be changed. All right. And the nearest measured formation distance, all right, I go to the top reservoir, right? So the nearest measured formation distance will be 0 because now my top perforation will be at the top section of the reservoir. So top perforation will be at the top reservoir, so the distance will be 0. Vertical permeability still 14.1. And now after I do additional perforation, the open interval is increased from 32 to 48. And it decreases the limited entry skin. Previously, before the workover, it is, you can check, 21. Now we can decrease the limited entry skin, all right, down to 15. So yeah, you see, we get better productivity index because we do shift up perforation, we add perforation, and we go to the top, we minimize the distance from the reservoir, distance between the perforation to the boundary of the reservoir. So we reduce the limited entry skin. That's better. That's good. Deviation skin, still the same. No change in deviation, no change in vertical permeability. The same perforation diameter, shot penetration. We do the same perforation technique, shot density, shot facing, and now we use again the Tariq. All right, and measured skin, previously it's 5, so we can use that. But yeah, maybe you can also think that after we do the workover, after we do the additional perforation, the crush zone skin will be reduced. So you can assume it to be 0. So the productivity index will be 7. But I think to manage expectation, we can still maintain the measured skin. Okay, to manage expectation to be more conservative, maybe. All right, so we assume that the productivity improvement comes from limited entry reduction by the perforation, by the additional perforation, by the workover. All right, so we maintain all the parameters, including the measured skin, and we change only the limited entry skin because we do additional perforation. So now, by the perforation, we can increase the productivity index from 3.2 up to, wait a minute, 4.9, which is a good news, right? I save, so we can check the show composite IPR. This green IPR is not a real IPR. It's actually commingled IPR. So if you get the red one and the brown one, you will get this one. Okay, so it's the commingled IPR coming from these 3 section of reservoir of models. So it doesn't mean anything. So I will rather just color it white. So I I cannot see it because it's meaningless. And let me check the legend. All right. And the main thing will be here. Match existing Fogel, the red one. Okay. The IPR that already match the actual performance. So the red one will represent the actual IPR before the workover. And the brown one, the chocolate one, represents the IPR after the workover. So I change this one, right click, properties, maximum to be 3000, and the step will be 500. Apply. All right. Or maybe 2500 instead. Apply. Okay. Right. So here, this is the existing IPR with productivity index of 3.2. And now we can increase the IPR, the performance, the productivity index has been increased to 4.9. Very good. Lastly, we go to analysis and we can wait. Now it's quite easy. We can just click calculate with the outlet node, the pressure or the wellhead pressure of 140, 54.7, and we get the nodal analysis. The blue plot, the blue curve is the IPR. Okay, and the green one, the VLP. Okay. So here, the operating pressure, the flowing bottom hole pressure will be 535, liquid rate will be 1055, oil rate 42 stock tank barrel per day, water cut 0.96. Great. All right. You can also edit this one, property. If you want to make it thicker, just change the weight and other things as per your preference. All right. But the main thing is that by the additional perforation, we decrease the limited entry skin and we get the improvement in productivity index. Okay, so I think that's all. The main thing, the strategy here is to honor all the properties that you get from table, from perforation table, from lock evaluation. You keep the permeability from well lock evaluation, and you do adjustment on properties that you have the highest uncertainty, and in this case is the crush zone skin. So I adjust that to get the same, the match productivity index with the actual performance. And after that, I can maintain the skin and I calculate the limited entry skin reduction, which leads to productivity improvement. All right, so that's all. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching and see you again in the next WellFlow videos. Thank you.